Welcome. In the last lecture, let us recap a bit. I introduced the concept of Brownian motion. Brownian motion, as I mentioned, forms the cornerstone of the theory of stochastic processes. So, let us review it once again very briefly. We started with the concept of a random walk, which is a sequence of discrete random variables, binary random variables that can take only two values, let us say heads and tails, and we had a sequence of those random variables representing a stochastic process, and then we extended that sequence to a continuous framework. So, we found that in the case of the discrete set of random variables, if we have n random variables, the mean obviously turns out to be 0 and the variance turns out to be equal to n. Then we said that no, because we want to model the stochastic process as a continuous process in time by reducing the step size, the time step size, or increasing the number of steps towards infinity, and that will blow up the variance, that will curtail its utility as a modeling tool. And therefore, we changed the jump dimensions. We started with a jump dimension of plus minus 1, we changed the jump dimension to plus minus under root t upon n. So, let us recap the entire set of assumptions that we had at that point in time. We started the process at the origin. So, we wrote W n 0 is equal to 0. Incidentally, W n represents the spectrum of values at time t, which is given by the argument of W n. N represents the number of steps. Number of steps was n, therefore, the layer spacing or the time step was t upon n, and the up and down jumps were under root t upon n plus and under root t upon n minus. Probabilities, because we were considering an unbiased random walk, the probability in either case was equal to 1 by 2. Then this new random variable which we termed as yi, and we had a sequence of these random variables for which we proceeded to take the limit by using or by invoking the central limit theorem. The entire sequence of random variables is captured by the displacements at any point in time is captured by the sum of these random variables. As you can see here, W n of capital T is equal to summation of all the random variables representing the fluctuations of the system or the transitions of the system at each time step. And then we also worked out that for an this is for the total evolution that I have just discussed. For the case of an arbitrary time t, small t, that is in between 0 and capital T, in between any point or observation point within the total or the overall time of the evolution of the system, we find that the number of steps turn out to be n small t upon capital T, and accordingly the results get modified, the variance gets modified to small t, and the mean of course remains 0. Then we did the limit taking. When we did the limit taking, we found that because of the central limit theorem, this expression that I have here becomes normally distributed as a standard normal variable, and because it becomes normally distributed as a standard normal variable and mu in our case is equal to 0, sigma square in our case turns out to be t upon n. Therefore, we find that W n, or now of course, I will use the term W infinity and ignore infinity. So, we will call it W t. W t is normally distributed with a mean of 0 and a variance of small t. This is a very fundamental result. This is the defining property of Brownian motion. The possible values, the spectrum of values that the Brownian process can take at any point in time is normally distributed with a mean of 0 and with a variance equal to the time elapsed since the origin of the Brownian motion. So, a quick recap on the properties of the Brownian motion. Brownian paths are continuous, although they are not differentiable at any point, and they are nowhere differentiable, to be more precise. The Brownian motion is normally distributed, or Wt is normally distributed with a mean of 0 and a variance of t. In fact, the increment W s plus t minus W s is also normally distributed with a mean of 0 and a variance of t. We can represent a Brownian motion or an infinitesimal increment of Brownian motion dWt in terms of the standard normal variable z and under root dt. It can be verified very easily that the mean and variance of both the sides turn out to be the same, and because in the case of a normal distribution, it can be completely specified by the specification of the mean and the variance, the two terms on the equality holds. Brownian motion is a fractal, as I mentioned earlier. Then we talked about the diffusion equation, and we found that when we start with certain fundamental principles like the collisions of a Brownian particle, random motion of a Brownian particle due to collisions that it encounters when immersed in a fluid due to the molecules of the fluid colliding with the Brownian particle, can be represented by a diffusion equation. And indeed, when we solve this diffusion equation, we arrive precisely at the same result as in the case of Brownian motion, which the probability distribution clearly shows, the PDF clearly shows that it is a normal distribution with a mean of 0 and a variance of t. So, that is where we concluded the topic of Brownian motion. Today, we will extend concept of Brownian motion and use it to define a path integral arising out of the solution of the diffusion equation. So, let us start with the one dimensional diffusion equation. Del phi upon del t is equal to u phi plus d upon 2. D is a diffusion constant, it is a constant, that is the most important part, and del square phi upon dx square. The solution can be written as it's quite simple. Solution you can write in the form of phi of x t is equal to exponential of this expression in phi of x 0. You can see that this expression that I have enclosed in the green box represents a kind of an operator which, operating on phi x 0, transforms this to phi x t. This is the function of what we call a propagator. We shall be talking much more about this concept of propagator when we talk about field theory, but for the moment its job is to transform a given state from one point in time to another point in time, and that is precisely which is explicitly shown by this equation here. We represent it by delta. Now, this expression, the propagator, the expression for the propagator, the exponential term, we use Trotter's formula to simplify it further. What is Trotter's formula? Trotter's formula is given here. Exponential of t into a plus b is equal to exponential t a upon n, exponential t b upon n to the power n by with the limit moving towards infinity. Limit n tending to infinity, exponential t a upon n, exponential t b upon n. To make this result applicable, we make the substitution: a is equal to u, b is equal to d upon 2 del square upon del x square. Making these two substitutions, we have our given expression for the propagator. Delta is equal to limit n tending to infinity, exponential t upon n into u, exponential t upon n d upon 2 del square upon del x square to the entire thing to the power n, and then with the limit n tending to infinity. Our job is to simplify this expression to the extent we can do. We shall be focusing on the second factor to start with, exponential t upon n d upon 2 del square upon del x square. Let us start with this expression. Now, to simplify this expression, let us recall a result in Gaussian distribution. If you look at this integral under root a upon pi integral minus infinity to infinity dy exponential minus ay square plus by, this can be simplified by converting it to a perfect square and then using the Gaussian integral, and we find that this result that we get is exponential b square upon 4a. Let us make the substitution. A is equal to 1 upon 2d, that is small a is equal to 1 upon 2d, b is equal to under root t upon n del by del x. We make the substitution in this particular expression. When we make this particular substitution in this expression, we get the expression given in the top green box, that is what we wanted to simplify, exponential t upon n d by 2 del square upon del x square. This is the expression that we get. If I put a is equal to 1 upon 2 d, this can be easily verified straight away. A is equal to 1 upon 2 d, b is equal to under root t upon n del by del x. So, b square upon 4 a comes out to be this expression precisely. Therefore, making the same substitution on the left hand side, I get this expression, that is 1 upon under root 2 pi d integral dy exponential minus 1 upon 2 dy square plus under root t upon n y del by del x. This, in a nutshell, what has happened is the expression that we started with has now been converted to an integral given on the left hand side of the last equation on the slide. The important thing to note here is, number 1, that the second order derivative appearing in the exponential has now been converted to a first order derivative. As you can see on the left hand side, this expression, you can see that it is a first order derivative. The second order derivative has been converted to a first order derivative, number 1, and number 2, which we will come to in just a moment, that this gives the feel that because when we have the first order derivative here and we have the exponential here, the relevance of this expression we come into the next in the following slides. So, this is what we have to start with. Now, as I mentioned earlier, what we have been able to do is we have been able to replace the second order derivative with the first order derivative in the exponential. That rings a bell. What bell it rings? Let us come to that. Now, this expression 1 upon under root 2 pi d exponential, this whole thing, if you look at it carefully, it can be segregated into two parts. The first part exponential minus 1 upon 2 d into y square, and the second part exponential under root t upon n y del by del x. You can look at it this way, that this is a random variable. Under root t upon n y del by del x is a random variable. You can look at that. Indeed, if we go back to the slide, if we go back to this particular slide where we have used the Gaussian distribution, we clearly find that y is actually a random variable. So, this because y is a random variable, under root t upon n y del by del x is also random, and we can look at this whole expression as a expectation value. Expectation value of what? Expectation value of omega exponential under root t by n y del by del x. This second part with respect to the probability defined by the first term minus 1 upon 2 d y square. You can see that this is Gaussian. Exponential minus 1 upon 2 d y square, and you have a factor of 1 upon under root 2 pi d also outside the integral. This is clearly a Gaussian probability distribution. So, we have a Gaussian probability distribution and we have a Gaussian variable, and therefore, the whole integral can now be represented as an expectation, and that is precisely what we are doing here. We are writing this as the expectation value exponential under root t upon n y del by del x. This brackets represent the expectation value. I have been using E factor as operator as the expectation so far, but this is also the same thing, precisely the same thing, whether I use these angle brackets or I use the E operator, it amounts to working out the expectation of the quantity within, and this is precisely what is to repeat this. In fact, if you work out the other way around, it becomes more clear. If you work out the expectation of this expression which is within the angular brackets, this is my random variable, and the probability distribution is given by exponential minus 1 by 2 d y square. 1 upon under root 2 pi d, which is Gaussian, and you are integrating over all of value of the random variable y, and therefore, this whole thing becomes the expectation value that we capture in these angle brackets, right. So, now let us look at, now you see we have simplified exponential t upon n d by 2 del square upon dx square, and what have we shown it to be? We have shown it to be the expectation exponential under root t upon n y del by del x. Please note this very carefully, that we have a first order derivative within the expectation, whereas the term that we started with was a second order derivative in x. Now, but we have to do more, we have to work out the nth power of this expression. In order to work out the nth power of this expression, in order to simplify the nth power of this expression, we introduce n such variables or n such expectations, and for that purpose we introduce n such variables y 1, y 2, y 3, y j, and with respect to each such y variable we take the expectation of one factor within this total of n factors. So, when we do that, what do we get? We get this expression in the green box right at the bottom. The limit n tending to infinity is still to be taken. So, that remains outside. Product j equal to 1 to n exponential t upon n u will recall that we had this term to start with. So, no change in this particular term, and the t upon n d by 2 del square upon del x square to the power n is written as a product of n random variables y 1, y 2, y 3 together with the expression under root t upon n d by dx or del by del x. So, this expectation, this expectation over n random variables, each of which is Gaussian, each of which is independent of the other, is represented by this limit n tending to infinity product of the expectations. Now, because they are all independent, so E x E y is equal to E x y. So, you can write it in this form, or you can write it as expectation terms, product of expectation terms or expectation of product terms. It comes to the same because they are independent of each other. The y i's are independent, y 1 is independent of y 2, is independent of y 3, and so on, right. So, some important observations with respect to the last expression that we had on the slide, the green box expression. Let us go through those observations. The expectation bracket stands for all the n expectation values of Gaussian integrals. So, all the expectation values are covered within the product and the angular brackets. In each term, the product with a lower index y I, that is y 1 will come first to the right, then y 2, then y 3. So, the order is increasing from the right to the left, this is by convention. The lowest y I, that is y 1 is represented at the first term, and the y 2 at the second term, and so on. The order is taken in the ascending order, right. Then you can look at this. As I mentioned, you can have all the terms within this expectation, or you can have it as a product of expectations. If you have it within the expectations, then what will I have? I will have a term in y1, then I will have a term in u, then I will have a term in y2, I have a term in u, I have a term in y3 and a term in u, and so on. So, they keep on alternating, y and u keep on alternating with each other. Now we come to the point that I mentioned earlier, that when you have a first order derivative in the exponential, it becomes very interesting. It becomes interesting because this acts as a translation generator. Now, translation generator means this equation holds. This equation is a variant of the first equation. The first equation clearly exemplifies the translation property of exponential alpha del by del x. When exponential alpha del by del x operates on any variable psi of x, it simply gives you the variable psi x plus a. That means, it shifts, it makes a translation shift from x to x plus a. The operation by this variable exponential alpha del by del x simply shifts the underlying variable x by an amount of a, and we get the new function at the new point phi of x plus a. On this basis, we get the second equation that we are going to use, exponential alpha del by del x exponential f x is equal to exponential f x plus a exponential alpha del by del x. This is simply an extension of the first equation that we had here, that I just explained. So, del by del x acts as a generator of infinitesimal spatial translations, and exponential del by del x does a finite translation, accumulation of infinitesimal translations. Why do we need it? Let us look at this. What we can do by this is, as I mentioned in a previous slide, when you look at this, you have alternating terms of y and u, y and u, y and u. We can bring all the y terms to the right hand side and all the u terms to the left hand side by making use of this property of being a translation generator. So, that is where the role of this translation generator comes into play. Let us see this explicitly. So, we have this expression exponential, this is an example how it operates, exponential t upon n into u x, exponential under root t upon n y 2 del by del x, exponential t upon n u x, exponential t upon n y 1 del by del x. Now, I have combined the terms, two middle terms. The two middle terms means exponential under root t upon n y 2 del by del x, exponential t upon n u x. This pair of terms, I will change their order. I will change their order by making the use of the property, the translation variant property of exponential t upon n u x. By making this use of this property, the translation generator property of exponential t upon n u x, I will reverse the order of the appearing of these two quantities. Let us see how we do it. And the property, as I explained earlier, gives us exponential alpha del by del x, exponential f x is equal to exponential x plus a f x plus a exponential alpha del by del x. In our case, what happens? We write alpha equal to under root t upon n y 2, alpha is equal to under root t upon n y 2, this particular portion, and we write f x is equal to t upon n u x. By making these substitutions and making use of the first equation, the red box equation, we simply arrive at reversal of their order. The del by del x term and together with the y 2 term now shift to the right hand side, and the u x term shifts to the left hand side. So, what do we have? This t upon n ux is as earlier, no change in that, but when this ux term shifts to the left hand side, it will have an additional factor of alpha, as you can see in the first equation, in the red box equation. Therefore, instead of ux, we will now have u x plus under root t upon n y 2. That represents this particular alpha here. As you can see, we have used x plus under root t upon n y 2, and under root t upon n y 2 is our alpha. So, f of x plus alpha becomes exponential t upon n u x plus this particular expression, which corresponds to alpha. And now, this derivative term moves to the right, and on the right we have the two derivative terms together. We have under root t upon n y 2 del by del x and under root t upon n y 1 del by del x, both with exponentials, of course. Now, little bit more simplification, simply adding the exponents, we get this particular expression. If when you add the exponents, you get t upon n u x plus t upon n u x plus under root t upon n y 2 e to the power x e to the power y is equal to e to the power x plus y, and similarly here we use the same thing, e to the power x plus e to the power x e to the power y is equal to e to the power x plus y. Right. So, now we bring another pair of terms into the picture. We bring another pair of terms in the picture. What are they? T upon n u x exponential under root t upon n y 3 del by del x, and whatever is there earlier is retained. When you again apply the translation generator, what we end up with is this slightly extended equation. We have exponential t upon n u x t plus t upon n u x plus under root t upon n y 3 plus t upon n u x plus t upon n y 2 plus under root t upon n y 3, this is, and now again all the dy by dx terms come to the right hand side, and we have exponential under root t upon n y 3 plus under root t upon n exponential y 2 plus under root t upon n y 1 with d by dx or del by del x common throughout. So, the net result is that by playing with or by making use of the property of the translation generators or using exponential t upon n u as a translation generator, we are able to transform all the derivative terms to one side and all the u terms to the other side. That is the most important thing. That is precisely what we have done, and we get this ultimate result. Now, let us go back to our Gaussian integral. We had this Gaussian integral dy exponential minus a y square plus b y. When you simplify this, by completing the square, we get exponential b square upon 4a and dy exponential minus 1 by 2 under root 2 a y minus b upon under root 2 a whole square, and that gives us this prefactor of under root t upon a. But the important observation from this is that this particular expression, that within the round bracket under root 2 a y minus b upon under root 2 a is a standard Gaussian or a standard normal variable, and it is distributed normally with a mean of 0 and a variance of 1. This expression, if I call this particular variable as z, then z is normally distributed with a mean of 0 and a variance of 1. Right. So, just to recall, z is normally distributed with a mean of 0 and a variance of 1. It is standard Gaussian, and putting a equal to 1 upon 2 d, b equal to under root 2 upon under root t upon n del by del x, as we did earlier, we get yj is equal to zj under root d plus d under root t upon n del by del x. This is simply we are making the substitutions. A equal to 1 upon 2 d, b equal to under root t upon n del by del x in this expression for zj, and then expressing yj in terms of zj. So, yj is equal to zj root d plus d root t upon n del by del x. Now, recall zj is standard Gaussian. Zj is standard Gaussian. So, let us look at the properties of yj. First, as n tends to infinity, what happens? Before I take the limits, let us look at the properties of each yj. Each yj, now the expectation of yj is clearly 0 when n tends to infinity. When n becomes very large, the second term tends to 0, the mean of the first term, the mean of z is equal to 0. Therefore, in the limit that n tends to infinity, yj has the expectation value of 0, because the second term vanishes when because it has n in the denominator, and as n tends to infinity, the second term vanishes, and as far as the first term is concerned, the mean of zj is 0, and therefore, the mean of yj is 0. What about yj square? Well, when you look at yj square, there is one term zj square d. Now, the mean of zj square is equal to 1. And what about the other terms? The other terms, if you look at it, when you square this expression yj square, the other terms will contain a factor of n in the denominator, either root n or n in the denominator. Therefore, all those terms will vanish in the limit n tending to infinity, and hence when we have these two values, the mean of yj is equal to 0, the mean of yj square is equal to d. So, this is important, and by the central limit theorem, what do we get? Recall, central limit theorem says limit n tending to infinity, sigma x minus n mu upon under root n sigma square is standard Gaussian. In our case, what happens? Mu is equal to 0, sigma square is equal to d. Therefore, our sigma yj or summation over the sum of the sequence of y's in the limit n tending to infinity, sum of the sequence of y's is normally distributed with a mean of 0 and with a variance of n d, because sigma square in our case is equal to d. Each y has a mean of 0, has a variance of d, therefore, summation yj is normally distributed with a mean of 0 and a variance of n d. We will continue from here after the break. Thank you.